Hello, welcome. This is analysis of algorithms. We're going to do the homework from chapter 2. Okay, so many of the questions are simple questions. We start off as follows. Use figure 2.2 as a model. Illustrate the operations of insertion sort on the array A. So we give this unsorted array, okay, unsorted array, 31, 41, 59, 26, 41, 58, okay? And the book has a very nice graphic showing how to do the insertion sort, and we want to do the same thing but with these numbers rather than those numbers. This is an easy question, okay? So basically it works as follows. You consider 31 to be an ordered thing. You compare these two, and 31 is less than 41, so you leave it alone. Okay, then the next one, 31, 41, 59, 26, 41, 58. Okay, again, here these two are ordered. You're comparing these two, they're okay, so you leave it alone. So then you have again 31, 41, 59. Yes. 59, 26, 41, 58. Okay, and so we're gonna, these are orders, and now you're gonna compare this. It's gonna go further. You're gonna compare it to this. No, not that. 20 to 46. It's gonna go over. You're gonna compare it to this. It's gonna go over, and then these all move forward. So this moves this way. This moves this way. This moves this way. I'm not doing it exactly like the book does because the book has different colors and different things. It's very nice, but something like that. Anyways, at the end of this is going to be 26 is going to go here, 31 is going to go here, 41 is going to go here, 59 is going to go here. Then there'll be a break, then you'll have the 41 and the 58. The 41 will compare to the 59 and the 41. Okay, it depends exactly how the algorithm, what to do with two equal things. So you'll look up in the algorithm, but the point is this is going to go forward, and so you're going to have 26, 31, 41, 41, 59, and then there's going to be a break, and then 58. Okay, all this is ordered, this is not ordered, and then you're going to bring this in here, this goes here, and so your final answer is 26, 31, 41, 41, 58, 59. Okay, so this was problem 2.1-1. Okay. Okay, very easy. You want such a question on the test. Probably too easy for a test question. Okay, next. Okay. 2.1-2, let me just read the question. Rewrite the insertion sort procedure to sort into non-increasing instead of non-decreasing. So they use that phrase. So basically it was going up, but what happens when you have two equal things? It was increasing, but what happens when you have two equal things? So we say it's non-decreasing. Anyways, now they want it to be going down, okay? So that's decreasing. Basically, it's as follows. I'm not going to rewrite it. You could take the entire algorithm, and there's one part that you have to change. Beforehand, it said A of I is less than key. By the way, that's interesting. Less than, not less than or equal to. Okay, so we don't have to, so that answers the question. In other words, you're trying to put the key in the right place, and you go further and further back until you find it at the right place. That's if it is going up, if the numbers are going up. Now we want the numbers to go down. We want decreasing. And so we change it like this. A of I, sorry. This is the way it was. Now we have it like that. So you can rewrite the entire algorithm and just change that one line. That's it. Okay? So that takes care of that. Okay. By the way, just doing this is not good enough. You have to write the entire line. Next. Okay. Next. 2.1-4. That's another problem. Let me just read it to you. It says as follows. Consider the problem of adding two n-bit binary integers stored in two n-element arrays A and B. The sum of the two integers should be stored in binary form in an n+1 element array. State the problem formally and write pseudocode for adding two integers. Okay, so I'd like to just, you know how to add two binary integers, I just want to do it again. 1, 1, 0, 0, 1, 1, 0, okay, plus 1, 0, 1, 1, 1, 0, 1. Okay, how do we do this? By the way, I'm going to consider this position to be, well, here I'm going to consider it 1, 2, 3, 4, 5, 6, 7. So I'm adding two 7-bit digits. Okay, 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus I'm sorry, 0 plus 1 is 0, carry the 1. 1 plus 0, 0, carry the 1. 1 plus 1 is 0, carry the 1. Okay, 1 plus 1 plus 1 is 1, carry the 1, and we go there. Now this is an 8 position. This is 8 bits. And so we have to worry about that. Okay, so that's how you add binary numbers. Okay, good. Now I want to write a program that does it. Pseudocode, an algorithm that does it. Okay, and so here's a nice way of doing it. Let's erase everything. Okay, this is not the only way of doing it, but I want to do it like that. What's the difference? I mean, any way you do it. Binary addition. Okay, it accepts two arrays, A and B, and the number n for the size of the array. Okay, okay, good. Now, first thing you do is you have to make an array for the third, a binary array for the third thing. So let C be an n+1 binary array. That's going to be the place where the answer goes. Okay, and so eventually the answer goes there. Okay, first thing, carry. We're going to need 1 bit for that carry. Sometimes it's a 0, sometimes it's a 1. Okay, we start off saying it's a 0. The first bit, you don't assume they had anything beforehand. Okay, now for I equals n down 2. Okay, so we're not going up, we're going down. And that's because if you think of the array like this, we went this way. We went backwards. So now, of course, it's a matter of convention. You can write it any way you want. You can do it the other way. You can have your bits going the other way. But I think it's clearer if we do this. For I is equal to n down to 1. So you decrement. You start at n and you go down to 1. Okay, great. Now, let's be careful about this. C could have n+1 bits. Okay, so we want to know where so C is going to could have the last bit. So we have to worry about this. Okay, and so we do it as follows. Ready? I have to put it into place. C of I+1. Okay, so I goes to n down to 1. C of I+1, that's going to be all the way on the last thing. Okay, and we're gonna go downwards like that. Okay, what's it equal to? Well, you have to add 3 things. A of I, the ith bit, plus B of I, the ith bit of B, plus carry. Okay, we started off assuming carry is 0, but we're not really. That's just for the first time you do the array. but all the other times is not so simple. And then, what do you want? Well, you want either 0 or 1, okay, but it should depend. Okay, and basically, what it is after you divide by 2, what's the remainder? So that's what you have. And just to remind you, 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 0. So, but here we could add in a third thing. So, okay. Anyways, this is wrong. Okay, I don't want to put in all the possible. I mean, that's right, but what happens if you put in the carries? The point is, when you add in all three things, if you get a 0, you should put out a 0. When you add in all three things and you get 1, you should put out a 1. When you add in all three things and you get out a 2, you should put a 0. When you add in all three things and you get a 3, 1 plus 1 plus 1, you should put out a 1. Okay? And basically, that's odd or even, that's exactly what it's going to do. So, if it's odd, I'm going to put in a 1. Okay, great. Now, next, you also have to worry about the next bit. Okay, so that's equal to A of I plus B of I plus the previous carry. Okay, and then think about it. Here you have to add a carry bit. Here you have to add a carry bit. So if it's larger than 1, so what we do is like that. If you divide it by 2 and you get out 0 or 1, you leave the carry as 0. And if you get out 2 or 3, you should make it 1. Okay? And that's it, except notice what this array does. It goes from n down to 1, and it fills in the I plus 1th position. So the last thing it'll fill in is the 2th position. Okay, so we need something for the 1th position. C of 1, this is outside the loop, is equal to carry. Okay. And then finally, return C. Okay, that takes care of that. This was 2.1-4. Okay, very nice. I like this thing because we know how to add binary numbers, but here we're just really seeing the nuts and bolts of it. Okay, good. Okay, next. Okay, so this is number 2.2-1, section 2.2, and that's the beginning of analyzing functions. So it says express the function n to the third divided by 1,000 minus 100 divided by n squared minus 100 minus 100n plus 3 in terms of theta notation. Now, we're going to get into this theta notation much more after we see chapter 3. We're going to do it exactly. But the main point that they want you to see is, look, these numbers grow, but there's nothing compared to the leading exponent. Leading exponent. Okay? And even though they subtract and some of them add, it's not important. The leading exponent is the most important thing, and the leading coefficient is not important. Even though you're dividing by 1,000, it's not important. So this entire thing is an element, and again, we're going to see it much more clearly in chapter 3, when we do chapter 3, of n to the third. So this number, n to the third, even though you divide, even though you subtract a lot of things, it's dominated by n to the third. It's going to be the same for that. Okay? So that's the answer to that question. Very simple question. Okay, next. Okay, consider sorting. Okay, consider sorting n numbers by first finding the smallest element of A and exchange it with the element A1. Then find the second smallest element of A and exchange it with A2. Continue in this manner for the first n-1 elements. Write pseudocode for this algorithm, which is known as the selection sort. So basically you're selecting the smallest, then you're selecting the second smallest, then you're selecting the third smallest, etc. What loop invariant does this algorithm maintain? What does it need to run for the first? Why does it need to run for the first n-1 elements rather than n elements? Give the best case and worst case running time of selection sort in theta notation. Okay, so before we do it, before we write the pseudocode, let's just go through a typical example. Okay, so here's 5 numbers, 10 numbers, 5 numbers. 41, 31, 17, 45, 29. Okay, so here's what it's going to do. It's going to go through all the numbers and find the smallest. Bum, 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 bum. It's going to assume this is the smallest and then compare it to that. That's going to make this the smallest. And then finally, this is going to be the smallest. It's going to compare 17 to 45, 17 smaller, 17 to 29, 17 smaller. So what it's going to do is going to swap this and this. And so you're going to get 17, 31, 41, 45, 29. Okay? Now, this is ordered. It's going to compare, find the smallest amongst this. So it's going to assume this is smaller, this is smaller than this, and this is the smallest, this is smaller than this is smaller than this is smaller than that. So it's going to swap these two, and you're going to get 17, 29, 41, 45, 31. Now it's going to go through these 3, find the smallest. The smallest is this. It's going to swap it with that. You're going to get 17, 29, 31. That's going to be the breakpoint. 45, 41. Now it's going to go through these 2, find the smallest. This is smaller than this, and so it's going to swap. Okay, and so you're left with 17, 29, 31, 41, stop, 45. Okay, and you don't have to search anymore because you know 45 is the smallest because it wasn't picked up. Every time you were looking for the smallest so far, it wasn't picked up because it's the largest. It's not smaller than anything else. And so that's it. This is called the selection sort. You select the smallest as you go along. Great. Okay, let's write a pseudocode for it. Let's write pseudocode for it. I did it already. Okay, it goes as follows. Selection sort. You give it an array and a number n. Okay, and you do the following. For I equal 1 to n minus 1. So this is your starting point of your searches. You're always searching for the smallest elements. You want to start. Where do you start? So you always start from the beginning, okay, and you go all the way to the n-1. You don't need to search. You don't need to sort. You don't need to search the last element because you know it's the last. It's the one. So I'm going to write that as a comment. Starting point of searches. Okay. Now, for each one, you write smallest index. You're looking for the smallest guy, okay? And he starts off as the first one you're searching for, okay? Great. But now you need another loop that actually does the search. So for j, you have I and j. For j is equal to I to n. What you want to do is you want to search from the first to the last, the second to the first to the last, the third to the last, the fourth to the last, the fifth to the last. That's what this is going to do. Okay? And here's what you basically do. If A of smallest index, okay, is greater than A of j, you're searching through all of them. You assume the smallest index is from the beginning, okay? And you're going to search through all of them, and if you have to change it, in other words, if this guy is smaller than this guy, if this guy is larger than this guy, then you have to change it. And you change it as follows. J is equal to smallest index. Okay, if you have to change it, you have to change it. Okay, when you finish searching this whole loop, okay, it's a loop with just one phrase. When you finish, then what you do is you swap, whoops, A of smallest index with A of I. A of I was the place where you started. You started searching in the ith position. So you now found here you find the smallest number, okay, and here you put the smallest number in the ith place. Okay. Okay, fine. And when you're finished, okay, that's this. Okay, when you finish everything, you return A. Okay, you're done. Okay, the loop invariant. Okay, now we didn't talk about loop invariant. I don't like loop invariants, whatever. But the loop invariant is basically that A of 1, A of 2, A of I minus 1. I'll just do A of I, are ordered. Okay, but at the beginning of each loop you have these guys are ordered, and then what you do is you add on that the I plus 1th guy is ordered also. Okay, question, next question in the book asks, why do you have to go till n minus 1? Why don't you do n? And the answer is, like I showed before, that 45, you don't have to go all the way because the last number was never picked up on any of these searches, which means it is the smallest guy, so you might as well just leave it there. Okay. How much work has to be done in the best case and the worst case? Well, notice what's going on. It depends what you're talking about work. If you're talking about comparisons, then no matter what, you're always going through these. So let's go through this. You have n minus 1 loops, and each one, so best case equals worst case, and just let's go through it. You're going through a loop n minus 1 times, so you have n minus 1, okay, and each one of them you're doing from there to there. So you're going to do, so basically it's the same thing as before, what we did. You're going to do n minus 1 plus n minus 2. Okay, the second time you're going to start at 2, so you start at that, plus n minus 3, all the way down plus till 2 plus 1. Okay, maybe you leave out that 1 over there. You don't really need that. Anyways, it turns out that that is, okay, about equal to n squared. Okay, really, the truth is it's n squared divided by 2. You're not doing so many, but that's so. We say we ignore these coefficients. Basically, in terms of theta notation, it's n squared. However, if you're also talking about how many swaps you make, so there it's a little bit different. Okay, so this is number of comparisons. Okay, and you're always making these comparisons, no matter what you're making the comparisons. But how many swaps you're making? Well, if it's totally ordered, best case, okay, number of swaps. Okay, if it's totally ordered, then the best case is 0. You don't make any swaps. Okay, if it's totally ordered. Worst case is n. Oh, I'm sorry, n minus 1. Okay, so that's it. So again, it depends what you mean by how much work you're doing. It depends if you're counting how many comparisons or how many swaps. Okay, great. 2.2.3. So this is a nice little algorithm. It's another sorting method. We're going to see like 7 sorting methods in our class. We so far saw insertion sort and we saw selection sort. So those are 2 nice ones. Section 2.2-3. The third problem. Consider linear search again. Okay, so we didn't do that. Linear search means I give you an array, I ask you to find an element in it. Okay? How many elements? So basically, let's do this a little bit carefully. You have a bunch of elements in an array. You're looking for a particular one. You try this one, 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 etc., until you find what you're looking for. Okay? Consider linear search again. How many elements of the input sequence need to be checked on average? Okay? Assuming that the element being searched for is equally likely to be any element in the array. So if you have n elements in the array, and so the element you're looking for might be here, it might be here, it might be here, it might be here, it might be here, etc., etc. So on average, okay, you're going to do n over 2 searches. Okay, the minute you find it, you stop. Okay. What are the average? How about the worst case? What's the worst case? Well, the worst case is you're searching for all of them. You don't find it here. 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 You find it there. So worst case is n. Okay, and that's why it's called a linear search, because this n is going to be a linear. That's the way we're going to learn in chapter 3. What are the average case and worst case running time of linear search in theta notation? Okay. By the way, what's the best case? 1. If you find it right over there. Okay. By the way, the worst case can happen in 2 ways. One, the thing you're looking for is right over there. Okay. And the other one is if you go through the entire array and you don't find it anywhere. So still that takes n. Okay. Okay. In theta notation, this is n. This is n. And this is 1. So that takes care of that. Okay, next. Okay. Okay. Two 2.3-1. Okay, so this is about merge sort. Okay, and the book has a beautiful graphic showing how merge works. It's on page 35 of the 3rd edition. That's a beautiful graphic. And we want to do the same thing for the numbers that they're given. So, let's just read the question. Using figure 2.4 as a model, illustrate the operation of merge sort on the array 3, 41, 52, 26, 38, 57, 9, and 49. Okay, so each one of these are individuals. Okay, this graphics is actually interesting because the way it's made is inverse to the way the program works. Because merge sort works recursively. Recursively takes a big problem and chops it into little parts and solves the little parts. Here we're looking at it from the little parts up. Okay, so let's do it. So you're going to merge these two together and you're going to get 3 and 41. You're going to merge these parts together and you're going to get 26 and 52. You're going to merge these parts together and you're going to get 38 and 57. By the way, this is already sorted, this is already sorted, this is not sorted. And you're going to merge these two together, and you're going to get 9 and 49. That's already sorted. Now you're going to bring these two together, and you're going to get 3, 26, 41, 52. You're going to merge these two together, and you're going to go 9, 38, 57, whoops, 38, 49, and 57. You're going to merge these two together, and you're going to get, whoops, 3, 26, 38, 41, 49, 52, and 57. So we're usually given this and we chop and chop and chop and chop till we get down. But the truth is, the way the algorithm works, the way the recursion works is, yes, it chops and chops and chops till you get to one element objects, and then you merge them in like this. Okay? And that's the final answer. Okay, great. That takes care of that. Okay. Okay, next. Rewrite the merge procedure so that it does not use sentinels, instead stopping once either array L or R, left or right, has all its elements copied back to A, and then copying the remainder of the other array back into A. So we didn't go through merge very carefully. We're going to do it a little bit later. Maybe we'll do it in class or something like that. But they have a certain way. I would like to just write the algorithm up and let you struggle with it on your own. So this is 30.2. Okay, so let's do it. Ready? Merge A, P, Q, R. Okay, so this is the beginning of the array, this is the end of the array, this is the middle of the array. Okay, and basically you have N1 equals Q minus P plus 1, N2 is equal to R minus Q. Okay, so what is this? Okay, let's go through it. Let L is going to be array from 1 to N, okay, and R is going to be an array from, from N to N1, and R is going to be an array from 1 to N2. So basically, you have two arrays. You're going to have two arrays. You're going to have A, okay, this is an array, okay, it's going to start at P, it's going to, I'm sorry, I made a mistake, okay, this is going to be Q, and this is going to be R. So this is going to be the midpoint, okay, and so basically, this is a sorted array, and this is a sorted array, and you're going to bring them together. This is going to be the size of the left side, this is going to be the size of the right side, okay. Let L and R, so just think of it, Q minus P plus 1, that's that, R minus Q, that's that. We have to worry about the pth element, which one does it go into, that's why you have this difference, okay. B, new arrays. Okay, first thing first, for I equals 1 to N, L of I equals A of P plus I minus 1. Sorry, let's add 1. For I equals, I'm going to make this a J. J equals 1 to N2. Okay, now we're going to fill in, here we filled in the left side, now we're going to fill in the right side. R of I, R of J, sorry, is equal to A of Q plus J. Okay, now, let's get some room here. Okay, we did that already. Let's do this. Let's continue. Okay, I equals 1, J equals 1. For K equals P to R from the beginning to the end. And here's what we're going to do. Okay, we're going to go through and we're going to put things in the left side or the right side. If I, if I is greater than N1, then A of K equals R of J. J equals J plus 1, else, so this is else, if J is more than N2, A of K equals L of I equals I plus 1, else, if L of I is less than or equal to R of I, A of K equals L of I equals I plus 1, else A of K equals R of J. J equals J plus 1. Let me show you what's going on here. Okay, first of all, you have two arrays. You put the left side of the array into L, you put the right side of the array into of A into R. Very nice. Okay, now what you're going to do is you're going to put L and R back into A, but you're going to put it very carefully. Okay, and you're going to keep track of how many of these guys went into these guys, how many of these guys went into that guys. Okay, how many guys? If I is more than N of I. Okay, so basically the brains of it is right here. We're going to compare the Lith guy to the Rith guy. That's the main thing. Okay, and we're always putting in the kth place. Okay, but every time we put in something, we're incrementing the counter. Okay, did we get to that point? Yes or no? Did we get to the I is the size of the left, and J is the size of the right. Okay, so we do. So if it's more than this, just put the kth place in. Basically, you have your array A, okay, and you have your array L, this is A, and you have your array R. And basically what you're doing is you're going through literally putting in these, each one of these guys one after the other. Okay? Now, here's the thing, if this is finished, then you just put in this guy. If this is finished, you put in this guy. If they're both not finished, that's this, then which one do you put in? You compare them. Okay? And if this guy is less than this guy, you put in this, you put in the left one. Otherwise, you put in the right one. Okay? It's a very nice thing. The main point is this comparison is done a lot less because once you finish, you don't have to put in, you don't have to do any more comparisons. So that's the goal. Okay. 2 more quick problems. Okay, it's a nice algorithm. It pays to do it with a bunch of cards and see how it works. Okay, finally. No, I'm sorry, not finally. 2 more algorithms. 2.3-4. Let's read the problem. We can express insertion sort as a recursive procedure as follows. In order to sort A through 1 through n, we recursively sort A 1 through n minus 1. So this is the insertion sort. You assume the beginning is sorted, and then you put in the new element. Okay? And then insert A of n into the sorted element. Write a recurrence for the running time of this recursion version of insertion sort. So it's very simple. Okay? Basically, you have n elements in your array. Okay? And you want to know how much work does it take to sort it. Well, the first thing you do is sort the n minus 1th of sort the first n minus 1 of them. Okay? And then you're going to put in the last one. Question: how much work is done in the worst case to put the last one in? Okay? And so if you think about it, here's your array. Okay? Okay? Here's your, let's say, n minus 1 guys. Okay? And you want to put in this nth guy. Okay? What's the worst case scenario? Well, you compare it to him, 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 you compare it to him. Okay? And if it's over here, each time this goes over here, this goes over here, this goes over here, this goes over here, this goes over here. Every time you do a comparison, you're also doing a swap movement. Okay, what's the worst case scenario? What's the worst number of comparisons you're going to do? And the answer is n. Okay, now that's it. So the worst case scenario is where you have to go all the way to the end. Okay, great. How much work is that? Well, it's going to turn out that's going to be, you're going to first time do n, then you're going to do n minus 1, then you're going to do n minus 2, and then you're going to go all the way down to 2 plus 1. Okay? And that is about n squared. Okay? So theta of n squared. Okay? We're going to see a lot more of this in chapter 3 and 4, where we talk about these recurrence formulas. Okay, last problem. Referring back to the searching problem, observe that if the sequence A is sorted, one can check the midpoint of the sequence against V and eliminate half the sequence. The binary search algorithm repeats this procedure, halving the size of the remaining portion of the sequence each time. Write pseudocode, either iterative or recursive, for binary search. Argue that the worst case is log of n, theta of log of n. Okay, I'd like to do that, okay, but I'll do it here. This thing is sorted by page number, okay? Let's say I'm looking for page number 721, okay? So I'm going to open up halfway to 699. Question: which way do I look? Do I look this way or do I look this way? Answer: 699. I'm looking for 721. I look this way. So then what I do is I take this side and I swap it, break it in half. I get to 1024. Okay, so now which one do I look for? Which of these halves do I look for? I throw away this half and I look in this half. Now I'm going to do halfway of this. Okay, and I get 848. I throw away that. Then I do halfway of that, and I get 796. I throw away half of that. And then I go 749. I throw away half of that. Okay, I get 726. I throw away half of that. I do 709. I throw away that half. I keep on chopping and chopping and chopping till I get to 721. Okay, so that's the way binary search works. I'm sure you've seen binary search, but let's do it anyways. So this is this is 2.35. So basically, let's just think of it this way. You chop and chop and chop and chop and chop, each time splitting the thing in half. Okay? Okay, how much work is done? And the answer is as follows. If you have n elements, okay, then what do? Well, then you do one operation, check, halfway through, check. And you see, is it on this side or that side? So you do one operation, and then what are you left with? You're left with n over 2 elements. Okay? What this means is that every time I can split the number, I add 1. Okay? Question, how much work is that? Well, it turns out that that's the logarithm of n. Okay? We write it fancy like this. Okay? Let me just go through a nice example. Let's say I have 500. If I have 500 elements, I'm going to split it to 250 elements. I'm going to split it to 125 of elements. I'm going to split it to 62 elements. Okay, 62 and 62 is 124. That's okay. Then I'm going to split it to 31. Then I'm going to split it to 16, let's say. Then I'm going to split it to 8, 4, 2, 1. So every time I split, I split once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times. Okay? I'm not being exact here because we have partial numbers, but 1, 2, 3, 4, 5, 6, 7, 8, 9. Every time I split, I added 1. So the log of 500 is about 9. Okay? But we want an algorithm for this. We don't just want to do it, we want an algorithm for it. So let me show you an algorithm. Okay, so this tells you how much work the algorithm does. Okay, I'm doing it recursively because it's the right way to do things. So let's do it. Recursive binary search. Okay. It takes a low and high. That's the low point of the array and the high point of the array. Okay, so I need, first thing whenever you do a recursive is how do you stop it? So again, here's your array A. This guy is low. This guy is high. Okay, and what we're going to do is we're going to chop it in half. Let's say we have to go here, so then this guy is going to be the high. Okay, then we're going to chop it again. Let's say this is the important one, so this is going to be low. And we're going to keep on doing that. Okay, so first exit strategy. If low is greater than high, okay, that means we went through the whole thing and we got these two lines got closer and closer and closer until finally they crossed. Then return nil. Nil means it's not there. Okay, we searched through it and we couldn't find it. Otherwise, mid equals low plus high divided by 2. Okay, that's the midpoint. Okay, we'll take the floor of that. Okay. If oh, I'm sorry, we're searching for K. K is the key. We're searching for K. If K is equal to A of mid, okay, that means you got the midpoint, you got it, then you found it, return mid. You're returning the position of what you found. You found your thing, return, get out of the loop, goodbye. Otherwise, okay, if K is more than A of mid, okay, so we have an array, we check the midpoint and we see it's in this side, okay, it's in this side, then return the exact same algorithm. It's a recursive algorithm, recursive binary search, okay, A, comma, K, that's the key that we're looking for, mid plus 1, here's midpoint, so we're looking at mid plus 1, okay, all the way till high. Else, if K is not equal to the thing that you want, and K is not more than it, then it must be less than it. So that, here's what we do. Return recursive binary search A, comma, okay, where? Okay, we're going to start at low, and we're going to go, oh, I'm sorry, don't forget to put K, we're still looking for that main thing, okay, and then high minus 1. Okay, and that's it. Okay, and this algorithm, every time it calls itself, it's splitting its input into two. How many times does it call itself? How many times can the input be split? And so we do that. So this algorithm works through theta of log of n. Okay, I hope you enjoyed it. I hope you did it beforehand. We'll talk. Take care.